you hear me? Yeah. Thanks for coming today. This might be a long drive for some of you guys. So today, I'm gonna walk you guys through the journey of Dreamer, and we will have this agenda where I'm gonna first introduce what it's all about, right? The picture, bring the word dream, all kinds of papers, and what is the idea behind it. And then I'm gonna specifically focus on the family of Dreamer. So this has 4 or 5 papers in series. And I want to spend most of my time in V4 because it's the latest and the greatest one. And we will have, of course, the hot takes at the end. So let's get started with the introduction. So, as you know, the word models as a term is not new, but it has been very highly popularized by the Dreamer series. And since it became a technical term in RL, it has been more than 7,000 citations. And some of the papers are literally using the dream in their papers. As you can see, some of the famous ones are Dream Zero, Dream Dojo, and so on. So all of these papers actually got the inspiration from this series. So that's why it's interesting. The lower horizon tasks. And Daydreamer is literally taking the policy and putting it on a robot, and robot is learning real time. It's very interesting, I think, so you can check it out. And as you can already imagine, so far we never talked about language or language conditioning. And of course someone thought about this and they just went ahead and incorporated the language into this schema. So there's going to be big focus on Minecraft. So I would like to give you guys an introduction on Minecraft. For myself, I have never tried it seriously, but I have friends playing it. So to be able to understand the difficulty of the task, you need to first understand what is the task about, right? First of all, we have a data set of more than 2,000 hours of contractor playing the game. It's almost around 200 million frames. And this is a medium-sized resolution, and the actions can be keyboard actions or the mouse actions. And you can see there is 20 unique tasks which is required for an agent to get a diamond. So here our goal is to get a diamond at the end of the day. And you might remember that in Dreamer V3 we also actually saw the Minecraft, but there is a huge difference because you can see that in Dreamer V3 there is a much more simplified version of Minecraft is used, and a lower resolution we have encoded the inventory because originally you can see that our agent has an inventory, right? And in inventory it is all images, but if you can encode it, you are getting rid of the hassle of predicting what you have in inventory. So basically V3 was dealing with much easier version. So I would like to take a moment here because those of you who have some experience with RL might know that one of the main problems in RL is the credit problem, which means when you have a long task, it becomes very hard to reinforce your model because you don't know which actions help you, which actions didn't help you. So in this case, we have this very long horizon task. It's like 20 minutes of playing. Imagine today, the longest robotic tasks we have, like 5-10 minutes. There are of course exceptions, but so the idea is to solve a task which requires 20 minutes of interaction, and if you do everything right in 20 minutes, you will get the diamond. So in V4, the authors intended to solve this kind of problem in a very unique way. So this is based on my understanding. There is no official diagram of this sort, but I just tried to make it clear for myself actually. So they are describing 3 phases, right? And the first phase is learning the tokenizer and pre-training the word model, and the second phase is fine-tuning the work model and doing some imitation learning to get the policy started. And the final stage is basically tuning the RL algorithm. So tuning the actor using the RL algorithm. Don't worry about the details, it's just we're gonna learn the most important highlights from each. But I will probably share the slides, you can come back again and see the details there. So, what is the idea in phase one? Phase one is all about getting us started, right? Because at the end of the day, we have images and the videos as our input, and we have to compress them, right? Otherwise, you cannot do the pixels themselves. So here, tokenizer is doing that job. Getting the images through the encoder and decoder. We have this Z variable, which is around almost 84 compression ratio. And we are using this decoded, encoded image in the work model. So the work model is conditioned on this encoded image and the action. And these other two parameters are parameters related to diffusion. But at the end of the day, once we have these ready, you can get any image, take them through these models, and you're gonna get something out of it. So how about the work model? Because at the end of the day, that's the core of the architecture, right? And they are using diffusion transformer, which is around 1.6 billion parameters here. And they mentioned a couple of terms, which is not too common in mainstream works, but I will explain them briefly. So one of the terms is diffusion forcing. Diffusion forcing is basically idea to support generating the next time frame given clean or lightly noisy story. So imagine normally the idea is to get a clean image at the end of the noisy, but now we can get away with having some lightly noisy images as well, right? And the shortcut model is actually the very literal term. Here you can see the graph where usually we need to do a certain number of steps to do the noisy to get from noise to the target image. But at the end of the day, each of these steps are actually an inference time burden. So if we can reduce this burden, it's gonna significantly increase our chance of getting real-time inference. So here the idea is to condition the neural network not only on the noisy level, but also on the desired step size. So let's say you give me some noisy image and tell me, I want to denoise this on 10 steps. So my model works with that. If you tell me to do it in 5 steps, my model still works with that. So that's the idea behind it. Of course, there's a trade-off. You lose some quality of predictions, but once you do the optimization, it becomes very useful. So one general trick in all work models is that when we do the sampling, we want to do random sequences of subtasks because work model doesn't care about the task itself, right? Work model only cares about what's going to happen next. So if you purely sample examples in the optimal order, work model will have a bias towards only generating successful trajectories in the future. So to avoid this, you need to shuffle it very well. All right, so I think this is one of the interesting parts. Even though the work model is always conditioned on the actions, as you can imagine, there is so much data which doesn't have action labels. This is valid for Minecraft as well, because you can have random Minecraft videos from the YouTube, which would be useless for this approach if you take the vanilla version. But here, they do an interesting study where they use only 10% of the action labels and the rest is not labeled data. And they realize that even with the 10% of labeled data sets, you can get most out of the learning, right? So you can see in this graph. So only using 100 hours of labeled data out of 2,500, actually model's prediction is 80% recovered. So they conclude that most of the learning happens from the general videos. The actions help to align the final specific dynamics of the downstream model. But here, you can see that to be able to solve this problem, if there is no action label, they use this learned action embedding But if there is actions, they just sum all of it and make it the action embedding. So at the end of the day, the model works with both labeled and unlabeled actions. So we have somehow working word model, and we have a frozen tokenizer. Now, the idea is to connect this to the actions, because so far we just studied how to predict the next state of the verb. To be able to connect this to actors, there are two tricks they are doing. First one is introducing the agent tokens. Agent token Q over there is basically one hot encoded tasks, right? Because we know there's 20 unique tasks, and we need to go through all of them in certain order and certain times. And we are just telling the word model that, okay, this is the task I am doing at the moment. But one thing to remember is that word model itself as a latent state, Z, doesn't care about the task, because whatever action you take, regardless of the task, you're going to observe the same similar next states, right? So here, the agent tokens attend themselves and the others, but the other modalities don't attend them back. And by giving the word model the information of the task, now we can produce another token, we call it H token. And this H token is called task output embedding. And we actually use this H token as an input to the actor and the reward function. So we are not directly using the latent state from the word model, but we are using this special token, which is more useful for learning the action model. As you can imagine, we are so far we are just doing imitation learning here because we have the action labels, we feed them here, and we get the actor and we get the output. Because we have the ground truth values for these, we can always do the mean square error loss and do the imitation learning. But how do we do the RL actually? So this is so far open loop, there is no feedback. So in phase 3, we freeze the word model because we want phase 3 to be very fast and real time. And for that, word model is the biggest model in this whole architecture. So idea is to fine-tune this actor based on these feedback loop. The feedback loop I'm talking about is this one. So literally, we have the word model unrolling the transformer with itself and predicting those tokens and predicting the actions. And we just feed predicted actions back to the model. So you can see this is, once you started with initial observation, this can go forever. This is actually what's happening. Very interesting thing here is that at this point, you don't need any data from the real world or offline data. Everything is going to be in imagination. So, a couple of things to remember here is that in this work, they're using a different RL algorithm because in the previous ones, they were just using soft Actor-critic. This PMPO is interesting because it lets you take advantage of both positive and the negative feedbacks. And as you can imagine, if you just purely operating in imagination, your observations are quite noisy. So you cannot simply rely on only positive feedback. You have to have more dense feedback, right? And that's the first part. And the second part is that you still need some guidance. If you just let your agent randomly imagine things, it's going to imagine everything but diamonds, right, at some point. So that's why we are using this previously trained actor from the previous slide, which was trained with imitation learning, as a somehow prior, and it is guiding or penalizing the loss function so that the agent is always doing something reasonable. Right? You can see you have the two coefficients here. So based on how much do you want to guide, how much do you want to bias your actor towards the imitation learning, you can play with the coefficients. So here everything is closed loop and everything everything is imagined. I think this is one of my favorite slides because this actually shows that even though you have the best idea, things are not very easy to implement, and you have to do lots of engineering tricks to get this working for the problem you have. So, quick question. So we have these three columns where we start with some training step seconds, inference, FPS, and the quality of predictions. And at the end of each of these small tricks, we're gonna have improvement in all of these. Which one do you guys think has the most room for improvement? And anyone thinking the training steps? Okay. How about the inference? Okay. Quality. So quality of the future predictions. Okay, I mean, it looks like many people think it's inference, but yes, it's inference. So here, you can see that we will check some of these tricks. We're not gonna deep dive into every single one of them, but idea here is that if you just take the vanilla model and go with it, it's not feasible to implement your agent in actually a real scenario. Here, after all these tricks, you get almost 6 times faster training, 27 times faster inference, and 5 times better video quality. So, if you check this first box, you will see that by simply reducing the sampling steps from 64 to 4, the model becomes 11x faster, which makes sense because we do 16x less steps. But this comes with a disadvantage of losing some quality. That's why this is where we introduce the shortcut model to recover the quality we lost in the previous step, right? So in the second one, another trick I like here is that they use these alternating batch lengths. The batch length is that you can think of it as in large language models, we have the window, the context window, right? And you can have a huge context window, but it will come at a cost of computation. So similarly here, you can have a context window of very long frames or short frames. So if you have longer prediction horizon, it's going to have more consistent predictions, but it's going to be very computationally heavy. If you have a very short window, you will have quick predictions, but it's not going to be very reliable and it's going to be noisy. So that's why they keep alternating with these batch lengths. And of course, this helps with training steps, because now you don't have to train very huge batch lengths, so you can get away with some small ones as well. So we got the 7x training steps here. So, okay, after we did all of these, how does it compare to existing algorithms, right? So, as I mentioned, the diamond challenge requires agent to go through all these 20 tasks, collect items, use them in search order, and after 20 minutes of interaction, if you did everything right, you can get the diamond. So there are a couple of other works which actually worked on this problem previously, and one of them is the most well-known one is the VPT, Video Pre-Training Model by OpenAI. This is one of the early works when OpenAI used to do some robotics work, and in that work they used 270 hours of YouTube data, some fine-tuning and lots of tricks, and then at the end of the day with some RL they can get some diamonds. When they don't do any RL, they cannot get the diamond. So as you can see here, the only algorithm that can get the diamond is actually the Dreamer. And even if you check the other milestones required to get the diamond, you can see that the Dreamer is just outperforming in every single task. And even without the phase 3, which is basically word model training plus behavior cloning, no phase 3, it is still beating the others, right? You can see here that without phase 3, it's still performing after. So it actually shows that every single part of the architecture matters a lot. So it is not simply relying on phase 1, 2, or 3. So how about the word model? Usually during the training, we don't care about the decoded images, but just to get a sense of what's going on in agent's mind, in the imagination, there is some interesting benchmark here, where they ask some human players to play the game in the imagination. So they give you the keyboard, you see what's going on the screen, but everything is neuron simulated, and you try to do tasks as a human player, right? To be able to get the tasks, your model should be able to simulate the game properly. And as you can see, some of the available open source models are actually very bad at this because they keep hallucinating very easily, and the players are confused. They cannot actually get the relevant items. So there is one large open source model. I'm not sure actually if it is open source, but in that one, there is some promising signs where players can get some of the tasks, but still very poorly, 5 out of 16. And for Dreamer, we had 14 out of 16, which is very promising. And the interesting part is, Dreamer is actually, it doesn't have a memory, right? Imagine you're playing a 20 minutes game, and you just have the last 9 or 10 seconds. And it is very hard to actually do all the tasks and get your final goal, because these last 10 seconds should always be very informing, and it should include all the information necessary to go for the next task. And other thing I like here is that this can be played in real time actually. So usually any kind of video generation nowadays is very slow, and playing this game in real time is possible thanks to these tricks in the previous slide. If you guys are interested, you can just go ahead, I think this one, link, I have the links there. You can try to play the game yourself and see how hard it is. So, until before, it was all open sourced, and there was a good community around it. But I think with the V4, which was closed source, some things are not so clear. So some of the things which were not clear to me or not mentioned in the paper is that, for example, they don't mention like how many steps of training, like what type of compute do we need for training, and what is these small tricks that you use during training, right? And what is the horizon of your imagination at the time? And as I said, how long does it take to train such a model, right? And on the other hand, there is some potential improvements, of course. And one improvement that comes to mind is that here we actually learn the word model and freeze it. But as we have better policy that interacts with the word, can we use these interactions to refine the word model in a way? That's, I think, one thing. And the other one is, obviously, if you had some sort of memory, instead of keeping the last 10 seconds, if we can just always have a memory buffer where we have the useful information, not blindly getting the last 10 seconds, this will help us getting rid of some of the compute burden of keeping the last 10 seconds, right? So that's the second way to increase this efficiency here. And of course, everyone would love to see some real experiments with the real robots. There are a few image generation examples in the paper, but there is no actual policy learning with the real robots. So based on this, we can have some hot takes, I assume. First one is that we keep seeing more and more approaches where the simulation is becoming more like a learned system, not an engineered system. So in the future, maybe robotics might just skip the classical sim pipelines. In this whole V1-4 paper, one pronounced thing is that once you have some offline data, you can use this for word modeling, you can use it for guiding your actor. So once you have the data, you're limited by the compute, actually. So this paper is very interesting because many people think that, oh, actually we have lots of compute, we just need more data for robotics, but this is another perspective for this problem. So far, prediction quality is still a bottleneck. Actually, it's not the prediction quality, it's the word model dynamics fidelity. So we are not still at a very reliable phase where we can just put these in robots and expect them to do things in imagination. And of course, as I mentioned in the previous slide, this probably still requires some sort of memory and more structured understanding of the word. And probably I would expect to see some memory-based approaches coming soon. And for me, this is my personal take on. So I see this as more like a robotic foundation model than just a simple RL algorithm for Minecraft, because this can be scalable. You can increase the data, you can increase the size of the architectures, and you can apply this to anything, literally. So for me, it's a foundation model. I think this was the last one. Yeah. If you have any questions, I will be around. Yeah, sure. I didn't include the 7,000 citations here.
Yeah, so I have a hot take as well. So we are trying to learn this world model to predict how Minecraft will evolve. But we also know that it's possible to programmatically express that, right? There is a Minecraft rendering engine that actually perfectly predicts. So I'm wondering how much of that affects the final quality of the world model, because you know that whatever that we are trying to predict is already programmatically expressible. And if you come to the real world, it's not the case, right?
Yeah.
Like once you take this out of this simulation world and then put to the real world, now there's an additional challenge that you are not sure if this thing is expressible at all.
Yeah. I think this is a good question. First of all, the fact that we know that Minecraft is predictable is very important, because it had actually one of our early reading talks, there was a VJ talk, and the slogan was "Predict the predictable." So if we are sure that this is definitely not predictable, it's going to be a radical application. I think in real-world applications, we know that there is some predictable part, but we don't know how much, right? How much is problem predictable versus how much is not. So I think my personal take on is that we should definitely be very smart on what type of problems we are trying to solve with this approach, because if you're trying to predict the not predictable, it's going to waste lots of computation and money.
My question about sort of translating the Minecraft entire stack into the real world, and since one of your hot takes is that maybe we don't need simulation. My question is that does that have a verifying requirement on the labeled data quality in terms of how the real world react to, for example, your action? Because if you don't have that kind of physical interaction, you're not getting the reaction. And right now, as far as I know, a lot of the heavy use case in simulation is still planning, right? Like, so if you do this trajectory, what would it fail the task, right? Like, so I think if you want to replace simulation with a world model, soft material interaction, those are still not there, right? So what's your take on that?
Yeah, I think that's what people call learning physics, right? So one of the known bottlenecks of this simulation is indeed physics, right? We cannot simulate these fine physics in simulation. I think we probably have a similar bottleneck for now in word modeling as well, because as you said, I might have a predicted future where I'm just touching an object, but if that object is soft, it's going to be a different story. If it's going to be hard, it's going to be a different story. So I think this is just a big debate still. I wouldn't be able to say one way or other, but it's still a bottleneck overall, all kind of simulation.
Can I follow up on if we go back a few slides on the comparison with the Oasis?
Which one is that?
The comparison against Oasis. Yeah. So could you comment on the different kind of model difference here?
Yeah, sure. So as far as I know, some of these are closed source, some of these are open source. For open source, they are mostly using diffusion-based models, as far as I know, diffusion-based models, because diffusion is very popular for any kind of image generation and video generation. But I think none of these are as transparent as before, so it's a bit hard to say what exact small details are there. But I just know that the engineering architecture is mostly similar to before.
Would maybe increasing the context to this context also?
Yeah, but okay, here's the trade-off, right? Probably they could increase it, but when it comes to real-time inference, you see that some of the models have like 2 FPS. Imagine you're playing a game with 2 FPS. So you wouldn't be able to solve the task for sure. That's probably why actually they cannot even solve the first one. Yeah, it's a trade-off. If you can find all these tricks which will help you free up some of your compute, you can always improve your context.
Is Oasis the work? Is Oasis the one that uses the word lab?
I think so. I think so. Yeah, I will be around for next 1 or 2 hours. If you have any questions or any specific questions for any part, I will be here. Thank you for listening.